So at this point, we're transitioning to the image processing portion of the protocol. So we have a couple images, and we need to calibrate our camera sensor so that we can have a wavelength scale in nanometers rather than simply just a pixel scale, which is intrinsic to the camera. So you're going to want to take your two photos that you took, so one of the CFL emission spectrum and one of the incandescent emission spectrum, and you're going to want to load them onto your computer however that's convenient for you. That can be coming off the cloud, which is the way that I do it, or you can connect your phone directly to your computer and then just drop them onto some directory that's useful. So I just have a couple here. I just put emission spectra here. And so you've got the two images. These are the raw looking images that came straight from the camera. At the same time, you're going to want to open ImageJ. If you haven't already, you're going to want to download that. There's a link to how to download this. It's freeware. This comes from the National Institutes of Health. It's really powerful open source software package that is used in virtually every field of science. I use this throughout my graduate school career. I use it currently for my research. It's a really nice tool to get familiar with. Really simple to use, but has powerful tools, especially for image processing. So if you do anything with molecular biology, you do things in biochemical analysis, analytical chemistry, environmental chemistry, this is the tool that gets used more often than virtually any other image processing tool because it's free, it's robust, and it's simple. So go ahead and download it, drag it onto your desktop or what directory you want to install it in, and open it up. And what you're going to get is just this bar sitting here at the top. So there's not a sort of a large graphical user interface. You just have a taskbar and that's it. And then what we need to do is load the images into the program. And to do that, if you were to load individual files, you could just drag and drop the image directly into the or directly on top of the taskbar, and that would open the image. In this case, we want to open up both of them as a stack because essentially what we want to do is we want high reproducibility of how we process our images. So we don't want to process individual images. We want to set a sort of a series of constraints and have those applied to all the images in what's called a stack. So in order to do that, we're going to go to File and Import, and then I'm going to click Image Sequence. And then you're going to want to navigate to the directory where you have your emission spectra stored. So mine are on the desktop and then in this folder called emission spectra. And so I'm going to grab, let's go to emission spectra. I'm just going to click the first one and then click open. And what that should do, if both of your images are in the same folder as they were with mine, it should prompt you with this new dialog that says sequence options. And so it should automatically identify how many images there are if those are the only images present, which is what you want here. So you can keep that as 2 images. Starting image is 1, meaning it's going to start with the first in the series, and it's going to increment by 1 image each, and it's going to keep them at 100% scale. Everything else you can leave as default. I'm going to click OK. And what you'll see is it loaded this image. But then now down at the bottom I have this slider, and the slider, if I drag it over, will drag it to my next image. So these are both of my images that I have loaded from the camera. Okay, so there's a couple things we need to do. The first is we need to sort of grab the region that we're interested in to process, and then we need to rotate it and align it so it's perfectly horizontal in the image. You can see here it's slightly askew by a few degrees. We need this to be rotated perfectly. And so let's start with the rotation. The way that it's easiest to do that is to go up to the taskbar, click Image, click or scroll down to Transform, go over to Rotate, and then you'll have this rotate dialog that will prompt. It may have grid lines as 1 as your default. I like to change this to 10. This is just going to set a series of yellow lines on top of our image. It'll be a lot more. It'll be a lot easier to identify whether or not the image is totally perpendicular or parallel to the x-axis. The other thing you want to do is click this radio button that says Preview. And what that'll do, you can see now the 10 grid lines that have been superimposed, and the angle has been rotated to 3.7 degrees. This is just because I was playing with this image before. This will probably default to 0 for you. So what you can do is, as long as the preview button is checked, you can click in small increments of 1/10 of a degree here, and what you're looking for, in this case, we're only concerned about this spectrum here. Probably the way that we'll use these spectrometers most in this class is not as a dual beam instrument, but rather as a single beam instrument. In that case, we're only concerned about this top spectrum and not about the bottom spectrum. So I'm attempting to align just this top spectrum, not worried at all about what's going on down here. In fact, we could just plug this if we wanted to just keep our lives simpler. And so you can see the bottom edge of this spectrum here is more or less parallel with one of these yellow lines at 3.2 degrees. I'm going to click OK, and then it's going to prompt me to say process all 2 images. There's no undo if you select yes. I'm going to go ahead and select yes. That's the whole point of us loading this up as a stack so that we don't have to do this individually. We get a reproducible set of stacked images. This is really important at this point to also identify, though, that you don't want to move your camera at all between taking these photos. That's why we have the Velcro installed. You don't want to position your phone every time. Otherwise, this spectrum is going to shift in the field of view, and then when you will try to apply the same rotation function or any other cropping features we do later, it's not going to work across all the images. So it's really crucial to just set up your phone for the series of images that you need or want to collect, and collect them without moving anything. You don't want to move your lamp, you don't want to move your cuvettes, you don't want to move anything. You want to keep everything as consistent as possible, just like you would do in a lab, and trying to maintain reproducibility and consistency across experiments. So I'm going to click yes here, and then I'm going to look, and what I can do is scroll between these two, and you'll see that both of the images have been rotated accordingly. Next, what I want to do, and this isn't totally necessary, but I just find it helpful for me to see, is I'm going to go up here to this rectangle function, the very first in the taskbar, and I'm going to just highlight. So I'm going to left click and hold and highlight over a large area of my spectrum, and I'm going to include space beyond the spectrum on the left, the right, and the top and the bottom. You can see there's excess space, several millimeters on all sides. I'm going to release the click, and that's going to hold my box there. I can always click and expand on any one of these vertices if I want to adjust this slightly. Then I'm going to go up to image, and I'm going to scroll down to crop. And what that's going to do is just cut away all the other stuff outside of that yellow box. That should be the case with my next image as well. Okay, so now I can go ahead and start processing the image. So at this point, what I essentially have is a two-dimensional set of data. Actually, it's three-dimensional. I have two-dimensional array of pixels. Those pixels correspond to the individual units of transistors inside of your phone sensor. So you've got millions and millions of them. Every single one of them registers an intensity of a grayscale, or a color in this case, but we really are only concerned with the grayscale. So you can imagine this is a three-dimensional image. We have an X and Y plane, that's the sensor, and the third plane coming into and out of the screen is the intensity or the brightness of each of those pixels. The brightness of each of those pixels is what we want to extract, because that's essentially the intensity of this spectrum. And so in order to do that, what we can do is take the rectangle function again, and I'm going to, in this case, now I am just trying to highlight the region of the spectrum, and I'm going to end where it's still black on both sides of my spectrum here. I can extend this out a little bit here, but I don't want to go too far right like this, because now I see a reflection, and that's intense, and that's not really part of my spectrum, so that's going to skew my data. So I want to end while it's still dark on both sides, and I want to crop the top and bottom so that I'm not collecting a bunch of this black space here. I want it to be just all of the spectrum. So this is a good set here. I can scroll over to this side and make sure, and you can actually see my phone shifted slightly. So this is poor experimental technique on my part, because this box is actually, it's pretty well aligned on this image, not as well aligned on this image. So what I'm going to do is actually grab this and pull this down slightly so that both of my images have plenty of only spectrum that's involved. Only the spectrum is within the yellow box. Okay, so now what we want to do is essentially average all of the intensities of each pixel in line vertically. So if you can imagine from the left to the right, there might be 1,000 pixels, 1,000 dots on the screen, each one of them registering some grayscale value, some intensity on the screen. What I'm essentially doing is taking everyone that's in a vertical line, and I'm averaging each of those vertical lines, so I get an average intensity, and then I'm going to plot that as a function of the pixel position, which is moving from left to right. That's the literal pixel on your camera phone. In order to do that, with the selected area, this rectangle, I'll now go up to Analyze, and then I'll scroll down to Plot Profile. And what you'll see here in my plot profile is the two-dimensional representation. Imagine we just drew a line straight across this spectrum and then plotted on the y-axis the intensity or the gray value, and on the x-axis we have the distance or the actual pixel number from left to right. So I said there are 1,000 pixels. Well, it looks like there's closer to 600, so there's roughly 600 points between the left boundary and the right boundary of this triangle. And then you can see as we move from left to right, we go from sort of low intensity in this dark region to a bright spot, which is the red band of our CFL bulb, and then we start to dip down, and then we go back up again, which is the green band, we go back down, we go back up again, which is the blue band, and then back up one more time, and that's the sort of violet band. So you can see pretty clearly those are the 4 individual bands. The problem is we have sort of half of a spectrum because we have the intensity, which is what we normally want, but the distance doesn't have any physical bearing in terms of chemistry. We need to convert this to nanometers, and that's what we're going to do next. All right, so next thing you want to do is open up a blank Excel worksheet here. So I've got a sheet here, and I need to take this data, this two-dimensional data, which is gray value as a function of pixel number, and I need to paste it into here. So I'm going to click on this very bottom part. There's this data option, and it says copy all data. So I'm going to click copy all data, and then I'm just going to click in one of these top cells here, and I'm going to do Control V or Open Apple V or just Edit Paste. And what you'll see here are the two-dimensional data that are represented by that plot. So that plot has our pixel number. So I'm just actually going to change this name to pixel number just so I remember exactly what that is. We'll shrink that down, and then gray value I'm just going to write as intensity because that's exactly what that is. It's the intensity value on a scale of gray. So we've got these data, and I'm going to write up here CFL, so I know that that's coming from my CFL. We can do the same thing for our second image of the incandescent emission spectrum. So I scroll over. I still have the same rectangle, position and dimension identical. You don't want to shift it. Remember, that's the whole point of doing this as a stack. So I'm going to take that data, and I'm going to go up to make sure I'm clicked on there and Analyze, and then I'll click Plot Profile, and you'll see that I get a pretty different looking profile as we move from left to right in this set of data. So I'm going to click now Data and copy all data here again. Then I will grab, maybe I'll put it here, and I'll change these names again. We'll just grab these names and paste them in, and then instead of CFL, I'll name this incandescent. Okay, so in order to calibrate this thing, we need to actually know what the specific wavelengths are for the CFL bulb that we see here. We see these bands. We know that this band is red, this band is green, this band is blue, and this band is violet. But how do we know exactly what the wavelengths are? Well, what I did was took this CFL and I put it into an actual spectrometer on campus today, and I did that also for the incandescent bulb. So now I have intensity, but I actually have the wavelength, the real wavelength here. So now we have data where we have the same intensities, but now with real wavelengths. And so now that we have this known data, we can set up a correlation here to convert the pixel number on this sort of theoretical axis to a true wavelength. So you can see here wavelength, remember wavelength, short wavelength is blue, long wavelength is red on the spectrum. So if we're looking over at our CFL bulb, this spectrum here is where these black lines or these peaks are. So this band right here that's just around 600, that's red, so there's our red band. This peak here that's around 550, that's our green band right there. This shorter band here, this dimmer one, is right around 500, that's our blue band right there. And then this peak here is the violet band right there. So what I need to do now is figure out exactly what wavelength is at each one of these peak bands, correlate that with where those bands are in pixel space, and we'll have a functional relationship and we can do a calibration. So let me show you how. Okay, so what I did was take the plot of the actual spectrum of the CFL bulb and I digitized the peak values for each of the colored bands. And so what I have here is the measured wavelength in nanometers of each one of these individual bands. So for the violet band, that one occurred at 435.5 nanometers. For the blue band, that was 486. The green band was 545, and the red band was 610. So I just took that spectrum that I showed you in the previous frame, and I just extracted those values straight off. So those are our calibration values. Now we need to find the associated pixel value on the phone. So if we look at this two-dimensional representation, the plot of the actual emission spectra, it's moving from left to right across our image. So this first peak here is the red one, the second peak is green, the next one's blue right here, and this fourth one is violet. So what we need to do is go into our raw data here, pixel number versus intensity for the CFL bulb, and we know that right around 100 or a little bit larger than 100 pixels, that's when we should be cresting for our red wavelength specifically. So what I can do is cruise down through this data, and what I'm looking for is a pixel that's around 100, and what we should see is the intensity rise and reach a maximum around maybe 120. So I'm going to cruise down here, and what I see is the intensity is going up. It's getting bigger and bigger and bigger and bigger. Now we're all the way up to 65, 66, 67, 68, and then it starts to go back down again, which is where this has crested. And so I want to grab the highest because that's going to show me my peak intensity and what pixel that was related to that value. So probably right here. And so if we're moving left to right, then that means this is the red the red band. And so I'm just going to go in here and I'm going to assign that red just so I remember. And I'm going to take the 116 here, I'm going to copy it, and I'm going to go all the way up here to my band color, which is red, which is the longer wavelength, and I'm going to paste that pixel number in because we're trying to establish a functional relationship between wavelength and pixel number. So we need to do the next thing, right? The green band here is at roughly, I'd say, like 240 pixels. So if I cruise down here, I should see that, and it should crest out, if I look at the y-axis, around 44 or so. So I'm going to go down to there. I'm going to look for a pixel 240-ish, and then I'm going to start to, yep, and then I see it get to 44, 44.1, 5. That seems to be my high point. This is the green band, so I'm going to take that as green. I'm going to copy pixel number 244 and paste it in. And what that literally means is the green band of the CFL lamp is landing on the centroid of the 244th pixel inside of your camera smartphone. Okay. All right. Do the next two. I'm just going to do this really quick. Okay. So I finished the last two bands, so the blue and the violet band. I grabbed those pixel numbers from the same data set, and now what I'm left with is the measured wavelength, which is in units of nanometers. as a function of the pixel number here. So what I can do is just make a simple XY plot of these two things. I establish a linear relationship between them. I'll extract an equation of the line in the form of y equals mx plus b, and then I'll be able to use that functional relationship to then convert the pixel numbers of each of my spectra and all subsequent spectra that I collect on this smartphone spectrometer. I can convert the pixel number to nanometers, which is what we want for a spectrum. So pixel number in this case is the dependent variable. It's the variable that it changes as a function of the wavelength, and so we're going to want to go to Insert, and we'll grab a chart and a scatter plot here. I'm going to right click on this scatter plot and click Select Data, and then I'm going to delete or remove the data sets that it thinks it wants to plot, and then I'm going to add my own. So I want, as my x values, I want to grab the wavelength, so I'm just going to grab those 4 values, and as my y dependent variable values, I'm going to grab the pixel number. That's it. I'll click OK and click OK. And what I have is a fairly straight line that represents the calibration between pixel number and nanometers. So I'm going to go through here, add axis title so I don't forget what I just plotted on my 2 axes. So this would be wavelength, or measured wavelength to be honest, as a function, and that's in units nanometers. And the dependent y-axis will be pixel number on the phone. I'm going to delete this series 1 because it's not important. I'm going to get rid of this. And then I need to add a trend line because I need to extract the mathematical functional relationship. So I'll go down to display equation on the chart, and I might as well toss the r² value on there. Okay, so that is my functional relationship between the pixel number of the phone and the wavelength. It's really important here to know that that pixel number is not an absolute number, and that wavelength is functional based on the relative position of that pixel number. If we go back to this square, this rectangle, this yellow rectangle, if I would have drawn this rectangle further to the left, I would have included more pixels, which means that pixel number here would no longer have correlated with the pixel number in the previous set. So that's why it's really important when you process images for data that's collected, you're processing them all together over the exact same pixel range. If you change the pixel range, then you've changed the calibration. So each time you collect real data, so you're going to have to do this every time, you're going to start by collecting an image like this of your emission spectrum for how you have your phone affixed to the spectrometer, and then you'll collect your series of data without moving your phone. That'll allow you to establish this functional relationship, and you'll do this for each of your experiments. Okay, so the graph is useful, and you can just grab these values if you want. I like to use a shortcut and actually just compute the slope and the intercept directly, so then I can use those values directly in the formula to compute my, my wavelength. So I'm going to type slope below here and say equals slope. This is a nice function. My y values were the pixels. I'm going to highlight those, click insert a comma, grab the second set, put a parentheses on there, and click enter. And then I'll do the same thing for intercept here. So equals intercept, and then grab the known y's, separate it by a comma, grab the known x's, finish with a closed parenthesis. And you'll see that my 2 values here, I'll put them in red, are the exact same values that come from the computed equation of the line here. But what's nice now is I can just grab these values and use those values directly as computed in a computation, which is what I want to do next, rather than having to transcribe them, which is always room for error. So I'm going to move these over, and then now the last step here is to convert the pixel number here into a wavelength. Okay, so I just made some space in my columns here because I'm taking pixel number and I'm converting that into wavelength, and I'm doing that for both of my emission spectrums. So I just created a blank column there and a blank column there, and now I just need to insert a formula based on this equation of a line to compute for x, because x, again, is the wavelength. on this x-axis, y being the pixel number. So I need to take the pixel number from this column of data, insert it for y, solve for x. So I will say equals, I'll put a closed parentheses. You don't really need it. I just do it for fun. Then I'll take my y value here, and so I'm plugging in the y value. I'm then going to subtract the intercept, right, because I need to get that onto this side of the equation. So minus the intercept, and that's the benefit of just clicking that now. I'm going to click F4, so that gives the dollar signs on my formula, so that as I drag this down later, it won't change that value. It'll hold that as a constant. I need to subtract that. I'm going to close that parenthesis, and then I need to divide by my slope, the minus 2.0183, to solve for x. So I'm going to divide by that number. I'll click F4 again, so that locks that, and then I'll click Enter. That makes some sense. That's a realistic number, so 665 nanometers, and that will allow me to just take this and drag this down through all of my pixels, and that will generate wavelength. So that means at the far right of my image here, at pixel 573, which is all the way to the far right, that corresponds to a wavelength of around 382, which is ultraviolet. And if I go all the way to the top, which is the left side of my image, that would be a wavelength of 665, which is on in the deep red part of the spectrum. So that works great. So I'm going to copy that one, and I'm just going to paste it right in here. I'm going to double click it to make sure it's drawing the right numbers, and it is. That's what's nice about Excel. And then I will click and drag this down until I get down to the bottom. And you can see the pixel numbers are identical, 573, and that's because we didn't change the rectangle size. If you were to change the rectangle size between the two or shifted it in any way, these wouldn't match up, in which case that's a red flag for you that you've processed your image wrong. There's going to be a systematic error there. So what we have here now is wavelength versus intensity, which is essentially a spectrum. So you've created the spectrum. These are emission spectra right now, so we could just take these two data points or these two columns of data and plot it. But as the protocol will tell you, to get this converted to absorbance, what we need to do is take the actual intensity that of a blank sample and divide that by the intensity of the true sample. That would give us the actual absorbance, which we could then plot as an absorbance spectrum. And that's what you're going to do in the next lab going forward when you quantify the concentration of dyes in some M&M candies. But this is the general calibration protocol and the image processing routine to convert the pixel number of your phone into an intensity. So you have all the tools. This is what you'd need to do every time you process an image. So my recommendation is to set up your phone, get it fixed in space, get your lamp fixed in space. First collect the CFL image right off the bat, because that's going to be necessary for this whole process. These values here aren't going to change. I'll give you these, the violet, blue, green, red bands that I measured. They're fixed because I measured them here. Then you'll go through, without moving your phone or your lamp, you'll install the incandescent bulb. So just be careful when you're taking out the CFL and installing the incandescent that you're not moving stuff. And then you'll be exchanging your solutions in the cuvette. You'll have your blank solution, then you'll run your series of solutions after that, collecting an image each time. And what that'll allow you to do is get the intensity as a function of wavelength for all of those solutions calibrated, and then you can compute the absorbance by taking the intensity of each of those solutions divided by the blank intensity at the same wavelength, just like you would on a spectrometer if you were doing this in person. I'll walk you through those things. It's a lot to take in, but you essentially have all the tools now to measure spectra with your cell phone.